So we're going to go through some of these problems on this first section of the assignment, and some of them we'll kind of skim over because they're a little bit repetitive, but you need some of that repetition to really get comfortable with some of these calculations. Question number 35 is asking you to, from the pair of, sorry, taking a moment to get a pen here. Taking from the pair, which is the stronger acid. And in A, this is the stronger acid because it is a strong acid. It's going to be stronger than water. And in B, you could probably guess that this is going to be stronger than water, but really what you do is look at the Ka and compare the Ka values and see that it has a larger Ka value, so it must be stronger. Here you definitely have to look at the Ka values of these two numbers. And you have to be comfortable with looking at this and saying, I know that this number is bigger than this number, so that you can identify that as a stronger acid. Number 36 is then continuing on with the idea of the stronger the acid, the weaker its conjugate base, or vice versa. The weaker the acid, the stronger its conjugate base will be. So chloride is kind of, it's such a weak conjugate base that even water is probably a more effective base or a stronger base than the chloride ion. So the conjugate base of strong acids are terrible bases. Water makes a more effective base. B, the conjugate base of a weak acid is a weak base. And C, weaker acids have stronger conjugate bases. Number 37. This is the equation you should use to solve for these. You were given hydrogen ion concentration, and so for all of these you do 1 times 10 to the negative 14 divided by whatever the hydrogen ion concentration is, and you're going to get the hydroxide ion concentration. Be sure you identify these as neutral, basic, or acidic. And think about why. Because this hydroxide ion concentration is this high, it better be basic. Number 38 was similar, except they gave you hydroxide ion concentration. So you use this relationship once again, the Kw for water, to solve for the hydrogen ion concentration and also to identify if it's basic or acidic. Let's see here, number 42, you were given probably the pH of most of these, and you had to calculate the hydrogen ion concentration from that, and maybe the hydroxide ion concentration as well. So there's several ways you could have calculated that depending on what you decided to use, and then identify if it's acidic or basic. Now notice in the last two, E and F, some people struggled with those as we went through them today. They struggled with them because they switched things on you. They're giving you pH, pH, pH all the way down here on A, B, C, and D, and then they gave you pOH, and so it was easy to miss that when you're doing pOH, you should get 1 times 10 to the negative 5 for the hydroxide ion concentration using this formula up at the top of this column. Anyhow, those answers should be right. They've been checked by a bunch of people. Look over your stuff and make sure make sure you can actually calculate all of those things. .44 you should be able to calculate easily, so practice on that. Let's see, 47. Trying to remember what this question is. Maybe, it's always good to look at these questions. Study the question. Pause this tape, pause this video, and look at the questions, because you've got to know what the question is to understand what's going on. 47 says, what are the major species that are present when you have HClO4 in solution? Well, HClO4 is perchloric acid. It's a strong acid. And so pretty much what's in species are these ions. And of course you've got water because it's in solution. Now water isn't going to contribute as much to the hydrogen ion concentration as this, so we're not going to worry much about water. In fact, for strong acids, remember, we calculate the pH based on the concentration of the acid. So here the pH is the negative log of 0.250 molar, or 0.602. And you want to check your sig figs and see, let's see, this was number 47. How many sig figs were there? It was 0.250. Yeah, so there are 3 sig figs. And this is 0.250 down here. And it should be 0.602 as well. So in 48, A and B, we're looking at calculating the pH of strong acids, hydrochloric acid in both of those cases. But in C, we're still doing hydrochloric acid, but they've changed something. Look how incredibly diluted this solution is. That's like the tiniest drop of hydrochloric acid in a huge vat of water. You could do the calculation and see, but it's an incredibly small, tiny value for the concentration. And so if you calculate, take the negative log of that number, you'll get a pH of 11. Oh, wait a minute, that's a pretty strong base. You can't get a basic solution by putting in a few drops of acid. What you have to realize is there's something present in addition to the HCl. There's water present. Water is the best acid present. So remember, when water is present, remember water is present in all acid solutions that we're dealing with. The hydrogen ion concentration in water is 1 times 10 to the negative 7. So in really dilute solutions, you can't ignore that. So in really dilute solutions of acid, the pH is based on water. So the pH here is going to be 7. Don't let that trick you. That's an excellent problem. It takes a lot of insight on your part to be able to solve that problem. It means you know some things. Yeah. Number 53, we now have a system where we have a weak acid. And we have a weak acid, we have water, we have some of these things present. This weak acid is the best acid present. It has a Ka value of 4 times 10 to the negative 4. So we can plug that into the icebox and calculate what X is. Now in this particular case, X is the hydrogen ion concentration, and you'll use that to calculate pH. And so that in this solution, pH is 2.